I will talk more about this subject of presenting operators in two different forms, the coordinate form that everyone is hopefully comfortable with, and this Bryan-Ket notation form that is somewhat more abstract. Okay, and we'll see how they go in one into another, and the bottom line will be that there are these two representations, and for the exact calculations, of course, they are identical. You can do either in one basis or in another. But for approximate calculations, you usually benefit from switching between representations. Okay, so again, the emphasis will be on the practical side. Then when you need to do approximations, then there will be some representation of the same problem, time-dependent or time-independent Schrödinger equation, which will be easier or will be kind of more efficient to do approximations for. Okay, so that's the idea that we'll end up with. Okay, so now, just as a reminder, the way we see operators, which I talked a little bit on the previous lecture, was okay. So say we take a simple operator that can be t plus v, right? And it has x representation, acts on the function, and then generates another function. So this simple quantum mechanics 101 type of representation can be substituted by more interesting that contains this Bryan-Ket notation. When we switch from the particular representation of these functions to their representation in a so-called abstract vector space, right, of the Hilbert space. Okay, so these guys, they can be later projected onto eigenfunctions of the position operator, and then they generate a familiar for us normal representation of these functions. Or if you do the projection on the eigenfunctions of the p operator, then they will be less familiar, but still you probably have seen this before. If you do the Fourier transformation, right, of x function, this is just a Fourier component. Okay, so and you can arrive to this from this again using the resolution of identity and Dirac's notation. One way would be to introduce this Dirac notation. Sorry, that's going to be x. Right, so this is our identity, and then we put it in between p and phi. Right, so what do we get? This is phi of x, and this is p of x function. So p of x function is the plane wave, phi of x is here, there is integration over dx, so that's the way to, yeah.
We have the triple x there, what is?
Okay, that
that's the same thing.
Yeah, that's the same thing, yeah. Yeah, so no triple x's, it's essentially this multiplied by this, right? So quickly you write it like this, right? Or you will see it a lot.
One day I'll get it the first time.
Okay. All right, so then you can represent your function either in x space or in p space, or you can represent it again in any basis of your convenience, right? So these are the coefficients essentially of the expansion that we usually talk about when we need to expand the function in some basis, right? So we can write the basis functions, the coefficients, right? And the way to obtain the coefficients was the integral over dx, functions multiplied by functions, right? And again, this all can be done through the same way by resolution of identity. Just to show this, if we do kind of phi of x, right? Phi of x is this. This is well. Actually, to get here, we're introducing the resolution of identity over these basis functions. Right? And then this is sum over n x fn. These are our constants. This is fn of x. Right?
Okay, sorry.
Yeah.
So we have the integral and the other product of the two x vectors, and then similarly over here we have the sum and the other product of the two. And so I'm having trouble remembering why that's the identity. Or
Why is this identity?
because that gives us the coefficient square. And the coefficient
That's right.
square.
The coefficient square will be, some of the coefficients will be always 1.
Yes. Okay.
Right? And also, that follows actually from the more fundamental reason is that these functions, they form a complete orthonormal set, right? So then you can represent, this is essentially what we're doing here is we expanding our function in a basis, right? And the basis vectors are these functions. In the functional space, like in the, okay, so let's just complete the analogy. Say you have a vector, right, v, and that's 3D vector, and you have also basis vectors ex, ey, ez, right? So then, what vector is? It's the vx component, which is a number, multiplied by ex vector plus vy component, which is again number, right? So say 5, 3, 1. Those are the vx, vy, vz components, right? But these numbers do not mean anything without definition of what the basis vectors are. Plus vz. Why is that? Because we can represent this vector as in some other basis. So we can say, let's now use different basis. Say e. Yeah, sure. Ex prime, ey prime, ez prime. I was thinking about more, drastic change. Like in that old joke, like let's take m. No, m is small. Let's take n. That's one of these jokes about abstract notation. Anyway, so this, prime may be not drastic enough, but believe me, those are the different vectors. Say ex prime can be ex plus ey, previous vectors, right? Divided by 1 square root of 2 to make things normalized, right? Then, how do we get these numbers if we have just a vector, right, and the basis? How do we get these numbers? Vx, vy, vz. If, say, we don't know them, well, then vq, x, y, or z equals to the scalar product or dot product of the eq with vq. Sorry, that's total vector v, right? And if we change now our basis to ex, ey, and z with primes, then we will get the.
And that's if the basis is normalized, right?
Sorry?
And their basis has to be normalized?
Bases have to be.
In order for that dot product to be equal to the component? Because if it's not, what to divide out by?
That's right, yeah. So you need to be more careful if its vectors are not orthonormalized. But whenever you have basis, then you can always orthogonalize your basis.
Yeah.
Right, and to normalize it. Huh?
Is that the Gram-Schmidt?
Gram-Schmidt process, right. And for Gram-Schmidt, Are we all familiar with Gram-Schmidt process? No? Okay. All right. Okay, so then Gram-Schmidt process, it's, okay, say you have two vectors. Okay, say imagine it's, could be 1, 1, and this is one vector in the basis of just the xy coordinate, ex, ey here and ex here, just the normal linear coordinates. And so we have vector 1, which is 1, 1, and vector 2, which is 1, 0, right? So they are, they can be used as basis vectors because they are well, kind of linearly independent, right? Because this guy doesn't have a y component, this one has, so they look like this, right? So one has a kind of x component, another has both x and y components, right? They are not linearly dependent because they are not collinear to each other, right? So then they are not on the one line, essentially, right? So this is not our situation. And so that's why we can work with them. But what we would like to build is, if we want to build the basis vectors, say ex, ey out of these guys, or something else, which will be orthogonal in the 2D space that would correspond to two vectors that are perpendicular to each other, right? Then there is a Gram-Schmidt procedure that does that for us, and all it needs is a definition of dot product. Why is that? Because dot product between the two vectors essentially define the cosine of the angle, right? So the dot product essentially defines what's the projection of the vector on the particular basis vector. So, and also dot product kind of through cosine defines what is essentially what does it mean to be orthogonal. So to be orthogonal, say if we do modification and these vectors become v1 prime and v2 prime, right? I am not specifying yet what the modification is. It's Gram-Schmidt that I will cover in a moment. But the orthogonality will be that the dot product is essentially 0. Why? Because the dot product corresponding to the cosine of, what is this, pi over 2, right? It's 0. Remember the cosine, if you have a 0 angle, then it's 1. If it's pi over 2, which is perpendicular, right, then you have 0. And this corresponds to cosine. So that's what we want, okay? Now, the way to get this would be, this looks like a good start as a basis vector, right? So v2, so we just form that v2 prime will be just v2, right? And then to get v1 prime, what we will do, we take v1 and then we subtract the projection of v1 with v2, v1. So let's see what does it give us. Now if we take v1 prime and do the scalar product with v2 prime, which is v2, what do we get? We want to get 0, right? So let's see what are we getting from this form. We're getting v1 v1 times v2, because v2 prime was v2, right? So we're getting this minus this we can taken from here, and here there will be v1 v1, right? So we're almost there. The only thing we need here is that this should be divided by v1 v1 to get rid of this, and then this will be cancelled by that, right? So to get the orthogonalization process, we need to have this. So what we do, we take this must be V2 as well, right? No, wait. Take V1.
And then you subtract off the component that's in the V2 direction. So we should have V2 over the top.
That's right. So there should be V2.
And that fraction is projection.
And then, right, V2 should be normalized. Right? Right.
I think it's V1, V2. I think that was right.
I think now it's correct, because then there will be V2, V2, and here there will be and here there will be V1, V2. Just a second. So we have V1. Let me do this algebra carefully. Let's say we would like to modify V1 prime. We take V1 and we subtract some component of V2. Okay, and then what we want to get is that V2 prime V1 prime will be 0. And from this condition, I will find what alpha must be. So V2 prime is the same as V2. We just started with V2 in this case. Then V1 is V1. V1 prime will be V1 minus V2. And here will be alpha V2. Okay. And so for this to be 0, what do we get? We get V2 V1 minus alpha V2 V2, right? So then from this, we can find that alpha equals to V2 V1 divided by V2 V2. Okay? All right, so then I can just substitute here alpha by V2 V1 divided by V2 V2, and here there will be V2. Okay? So this is the process. If we have two vectors, we start from some vector, and we make it our first vector. Then we take a second vector and we subtract the component of the vector we started with some coefficient that makes this scalar product to be 0. Okay, and we can do it indefinitely. Like if we have now 3 vectors, we can take the next vector and do similar procedure. Say we have V3 to modify. So we take the V3, and what we do, we subtract alpha of V1 and subtract beta of V2. So the way these are already orthogonal to each other, right? So the way we do it, we then find alpha and beta if we take V3, so say V1 project on V3, right? This must be 0, and the second condition is that V2 prime V3 should be also 0. Right? We already obtained these guys. This is our V2 prime, and this is our V1 prime. And so we want to correct our V3 by subtracting these components. And since we have two coefficients, two conditions, we can always satisfy them by the same logic. Here the alpha will be V1 V3 divided by V3 and then beta will be V2 prime V3 divided by V3. Okay, and so you can go essentially to the from 3 to 4 to 5 to 6 and so on and so forth, depending on the dimensionality of the space. So all you need to create an orthogonal set of vectors perpendicular to each other is the definition of the scalar product, because scalar product defines what orthogonal means. Okay, so then we go to functions, and with functions, well, how do you say one function is like how? What does it mean to say one function is orthogonal to another? Huh?
The inner product is 0.
The inner product or the dot product is 0, and then we need to define the inner product. That's why the Hilbert space is a linear infinite dimensional space with the inner product, because we want to have inner product to make our functions orthogonal to each other. Plus, this process actually, once you get the vector, and if you want to normalize, you always can normalize, again, using the dot product. If V3 prime is not normalized, then you divide it by V3 prime, scalar or dot product, inner product, square root, right? So then by definition, if you, this will be, say, V3 double prime, this V3 double prime, by definition will be already orthonormal. So if you have V3 double prime scalar product, you just put its definition, V3 prime divided by V3 prime square root and another square root of the same V3 prime, right? So then this is 1. Is that clear? Okay, good. So the same can be done with functions, essentially. And functions can be, well, make orthogonal to each other and orthonormal. And once you have orthonormal set of functions, then you can expand one function in a complete set. That's what we did here in this expansion, right? And that's very important for quantum mechanics because, say, the measurement process, how it works. You have, for any property, you have an operator. Operator has eigenfunctions. By postulates of quantum mechanics, those eigenfunctions form complete set, and they are orthonormal. That can be shown because operator is Hermitian. Functions corresponding to different eigenvalues of the Hermitian operator, they are orthogonal, and then you can normalize them always. So then you get orthonormal set, and that's why whatever wave function you have, it can be expanded in eigenfunctions of the operators that you measure. And so then that guarantees that if you measure something on a wave function of, say, phi x, then you will get the results corresponding to the eigenfunctions of eigenvalues of those eigenfunctions with the probabilities which are Cn squared, right? And if for every property we didn't have the complete set of eigenfunctions, then it wouldn't be guaranteed that our wave function could be expandable. Okay. So what could be an example? Well, a simple example is, say, the non-complete set would be the odd powers, right? So this is incomplete set because, say, x squared cannot be represented, or cosine cannot be represented because cosine contains the x squared in a Taylor series expansion. So, but the complete set could be if you also add the even powers into that progression, okay? And then every good functions, analytic function, then it has a Taylor series expansion, and that's your expansion. Now, this is a Fourier kind of expansion because you expand it not in the polynomials, but in some complete set of functions. Okay. All right. Now back to Dirac notation. Back to Dirac notation. So the operator, then the second form, how the operator can be presented, is through introducing of, say, some basis functions. I put chi, right, h. So there is a sum over I and j. This is essentially two resolution of identities. Sandwich the h, right? And then what this shows us, well, first, this has off-diagonal terms because h chi I is not necessarily chi I multiplied by some constant, so chi I is not necessarily the eigenfunctions of h, right? So, but then this form, what it allows us to do, if you have arbitrary function psi, then h psi should give us this phi function. And what is phi? And we can use this expression to show what phi is by putting the chi I now for, okay, I'll make short annotation in the second step. Right, so you have this. So this is a constant in expansion of phi in the set of chi j functions. This is just a number. So essentially, the operator became a matrix, right, in the basis functions. And then we have, just to preserve the dimensionality, we started with a ket vector. We end up with a ket vector because what operator does, it maps ket vectors to ket vectors, bra vectors to bra vectors, right? So that we should have this, then, and they're multiplied by a bunch of constants, hij, and then this can be called C, or C was there already, say dj. Right? So then you see that the summation here only over I for the ket, so the summation of the j can be put here. So you could have chi I and then di tilde, where di tildes are just summed over j, hij, dj, right? So the action of h on psi can be thought as first you expand your, well, I should put psi here. It's phi we're getting, but we start with psi, right? So what we do, we first expand psi in our basis, which is, well, maybe eigenfunctions of some operator I don't specify, just orthonormal set. Then we get the coefficients, and essentially we are transforming this information into the coefficients. And then the action of the operator is kind of transferred to the action onto the basis functions that we are kind of interested in using, chi's, right? So then the way operator modifies these functions is given essentially by the matrix hij, and this matrix is just a matrix of numbers, right? Because those are the integrals. So these are numbers, and they don't mean again anything unless you know what the basis functions are, right? If I give you a matrix full of numbers, then it doesn't represent the operator, as well as like if I give you 5, 3, 1, it doesn't represent a vector unless you know what the basis functions or basis vectors are, what this 5, 3, or 1 corresponds to, right? So you need to know what the basis vectors are. So the same with the matrix. The numbers itself, they don't mean anything. You need to have these functions to understand how the operator will work on any function, right? Sure.
So the x of I and the x of j are just two elements of some basis that we pick because maybe we're interested in.
Right. So say we are studying, to give you an example, say we studying the problem with particle in a box, and then the bottom is has an inclination, right? So then this is our Hamiltonian, and then we're using chi's, which are eigenfunctions of H0, and that H0 is a particle in the box Hamiltonian, right? So our chi-i's giving us Ei's chi-i's for H0, but H is H0 plus this potential, which is linear alpha x, right, inside the box. So these functions chi-i's, they're not going to be functions of eigenfunctions of H, so that's why these elements will be, well, will be non-zero even if I is not equal to j. Yeah.
And then my other question is, so if we have we have a chi j, for example, vector, if we take the outer product of it with itself, we always get the identity? Did you say that that's the identity?
If you have chi-i's which are orthonormal, then by definition, what orthonormal means is the delta ij, right? So then if we do the inner product, this is one identity, right? And you multiply it by another identity.
So that is the identity?
That is identity because 1 times 1 is 1, right? How do we see this? Simply, it's chi-i what is this? This guy is delta ij, right? And they have an ij summation, right? So then what did we get? We got delta ij that will kill every j that is not I. So we're going to kill one summation index, right? So then it will be sum over I only, and then chi-i. And this j will turn to I because that's the only survivor, right?
Is that the identity that thing you have left at the bottom?
Well, we said this is identity, right? This is identity. We summed.
That was my question. Is it always the identity like this?
Well, if your set is not only orthonormal but complete,
yeah,
then it's always an identity. If you sum over infinite number of states.
Okay. Yeah,
usually in functional space, you need to go over, well, infinite number of functions to be complete. So you can play with this on a problem particle in the box, right? So chi functions are particle in the box eigenfunctions, right? And then you can define any function you want that has zeros at the boundaries, right? And then you can expand that any function of your choice. My recommendation would be to start looking at, say, this function, right? So this function necessarily has zeros at x equals 0 and x equal L, right? And then this satisfies our condition, and then you can use particle in the box functions, which are square root of 2 divided by L, sine of n pi x L. So essentially nothing that looks like this, right? But you can go over them and form the linear, the scalar products or dot products with this function. There will be your coefficients in front of these functions to represent, and then you can start plotting. And actually,
is that your like initial conditions? That function is the x times x times L?
It's not initial condition. Initial condition usually is used to define your function for 0 time in a solution of time-dependent Schrödinger equation, right?
So what are we using that x times x minus L for?
As a function that you want to expand. So say this is your psi of x function. Let me just move this. Yeah. So you have this function. Then what resolution, or like what this resolution of identity would do, you take this function and do the expansion that psi of x is equal, right, to sum over cn's chi n's, right? And then cn's will be the integrals from 0 to L chi n x function psi. So you literally can take a MATLAB, plot this function, and then start plotting what you're going to get if you start adding terms in this expansion.
Okay.
Right? So you start with n equals 1, and 99% of the function will be already represented. This is, but if you want something more challenging, you put some powers. Right? Then it becomes more challenging to represent such functions. What you're going to get is that, well, the percentage of the first contribution will be smaller for those more intricate functions. And then, but if you start adding terms, n equals 2, n equals 3, n equals 4, these partial sums will represent the function quite well at the end. Okay? And so maybe that should be made your homework exercise. All right, so, okay, any questions on that? All right, so then we also discussed some eigenfunctions of X operator previously, right? So they can be used as basis as well in all these expansions. And this is important basis because it kind of bridges the two representations of the operator as a kind of as this object, right, in the Bryan-Ket notation, represents the operator as a matrix for some basis functions, and this more naive representation of the Hamiltonian as just an operator that acts within the X variables, right? So one way to connect this would be, okay, we can just go with the Dirac notation and introduce the resolution of identity for X, H, right, and then another resolution of identity okay, with, of course, X primes. So what do we get? We get H equals to dx prime okay. All right, now I'll show that this is the same as H of X, the one that we are quite familiar with. All right, so say for the concreteness, that's p squared divided by 2m plus v of x, right, which is right, so we'll obtain this from this. Right? So I would like to remind you this x basis, those are the basis functions for the x operator. What x does to them, it produces the x as a variable. This is operator acting on the abstract vector and producing the eigen value, which is also a variable, and then it gives you back the function. Okay, and we talked about this, that if you want to know what the spatial representation of these x vectors are, this require introducing the delta function. Okay, and one comment here that the Tanner book, which I highly recommend, the chapter 8 in linear algebra, that talks about some of this stuff. I think it has some troubles with definition. What is actually introduced as a definition, and what are the consequences? Because in one exercise, 865 exercise, and I don't give it anymore because I kind of found that I somewhat disagree with his point of view. That he asked to prove this statement. But to me, this statement is a definition of what these basis functions are. All right? So we usually, in abstract space, when we don't have, we start with some vector psi or x, right, or p. We don't have anything yet. We don't know anything. So how do we describe these functions? Well, we describe them, first of all, as eigenfunctions of some operator, right? And that's the definition. So this is eigenfunction. This can be rationalized. Why, if it's an eigenfunction of x, then this should be like this. And we did it last time, okay? But essentially, this is a definition, and this is a consequence. Now, what do we do with this? We will start treating the terms in the x representation. Here's how we do it. So essentially, we want to consider this first. Right? What is this? And the way we do it, we have p term, p squared divided by 2m. Right? And we have also v term. V is an operator. Right? So this one is relatively simple, because what we know about v as an operator, it's some kind of function of x operator, right? So let's say kx squared, right? Harmonic oscillator. So what happens is, no matter what function of x with a hat it is, right? It is usually an analytical function, so we can do the Taylor series expansion, and we can use this expression so that v of x acting on x will be v of x as a function of a variable multiplied by x. Okay? And so what we have here is x prime, and then v of x. Okay? And this is a delta function. So x minus x prime multiplied by vx.
And sorry, we can pull out v because it's just a real multiplication. Like, so essentially, it's just the operator of the potential energy is the real number that you're multiplying in. And so we can pull
well, in this abstract terms, v is a function of x operator, right? Mm-hmm. So what is a function of operator? Well, in this case, it's just for harmonic oscillator, it's x times x, right, divided by 2. So we know how to operate with x operator on the x. This is given by the definition of what this ket of x is, right? So we just formally apply x twice, and so what do we get? We get well, from one x and then another x, right? So what we will get is x squared x, right? And this is a variable now, not an operator. Okay? So if this more complicated function, then usually we still work with analytical functions. That means they are Taylor series expandable, right? And if you have Taylor series expansion of v of x as an operator, then you have essentially action of some powers of x operator, right? And it's easy to do powers, especially on the eigenfunctions. Okay? All right. So v is simple. We did it. And now p, actually can be treated as well using the following insight, that we will put the resolution of identity here in P eigenfunctions. So the purpose here is that we know how P acts on its eigenfunctions, okay? And it's usually always the case if you're dealing with operator, the easiest way, well, to understand the result of that action, to expand your function in eigenfunctions of the operator. Then operator will act on the eigenfunctions, and that will generate just eigenvalues times functions again, and then you'll get your result very quickly. So here's the illustration. So 1 over 2m can be put aside, and then you have p squared, and then the resolution of identity we introduce is eigenfunctions of p operator, right? And then you have x prime, right? Now, what do we have? We can put the integral again outside. And then what we have is x acting on p squared that acts on p x prime. All right, and then this is 1 over 2m. We have p. Every time p operator acts on p, it will generate p as a variable times p. So we have 2p variables, so it's p squared times p function, right? And then we have this expression, right? Now, these guys, we know them from well, the spatial definition of what p eigenvectors are, or eigenfunctions. So one is exponent of ipx, and another is exponent of minus ipx, because it's conjugated quantity, okay, with prime. So you have these two, and you integrate dp with p squared. Okay. All right, so now, no. This can be seen as integral of dp, derivative with respect to x twice of exponent ip x minus x prime.
Why do we have the derivative? Why do we get to turn the eigenvalues into the derivative?
Oh, the trick here is the derivative when it differentiates the exponent. All right, so what will it do?
You get ip times.
So the p will come down, right?
So
Twice.
Okay.
This is just another representation of the same thing, right? So when you differentiate, and I'm missing minus here, so because two i's will give you minus, right? So compensate for that minus, there is a minus dp second derivative of this, right? Now what is good about this is that we can put or essentially exchange the integral with differentiation and put the differentiation before the integral. Okay. And so we have 1 over 2m square dp okay, but this is one of the definitions of what delta function is. Okay, why is that? Because if you think about this integral, then for x, which is not x prime, right, there will be x not x prime, then there is some difference, and then you have essentially a summation over p, and this term will always have a counterpart that will cancel it, because we sum over all p's from minus infinity to plus infinity, right? And if we have an oscillation with some frequency going on, and frequency related to the difference between delta x and x prime, right? In that integral, there will always be something that oscillates out of phase, right? And then they will kind of cancel each other when you sum them together. And that's the x not equal to x prime. But when x equals to x prime, so the result of this integration will be 0. But when x equals to x prime, what we have here is just 1, right? Exponent of 0 is 1, because x minus x prime is 0.
That's isn't that one of the definitions for the delta?
Yeah, that's what I'm getting. Yeah, I'm just kind of explaining why is this a delta function. Okay, so delta function is something 0 everywhere and infinite at the x minus x prime equals 0. So I explain you why this integral will be 0 everywhere where x is not x prime. And then when x equals to x prime, it will be infinite, the integral, of course. Okay, so because for x equals x prime, you have 1 here, and you integrate for the whole space, and you get an infinity, because you have plus infinity minus infinity, so it's even 2 infinities. Although 2 infinities is the same as 1. Okay, so you have a delta function as a result, right? And what we have is 1 over 2m dx squared delta function of x minus x prime, right? And then we are ready to go back and represent this element, because we have both terms. Right. Can we switch the order of that? Well, we have an integration, right? And generally, we can consider the integration first, and then we'll get rid of x prime. Okay, or x, doesn't really matter. So this is a constant, this is acting on a function which is there, and what we're getting is plus, right, so that's delta function, yeah. So then what we're getting here is, if we go back to the total integral, right, h equals to 2 derivatives dx prime, we have in both terms x minus x prime, right, and we have minus h. Right. So then one integration will just give you identity, right? Because integral of the delta function will be just 1. All right, and then this will be the integral of it. And I forgot, what I forgot was the Bryan-Ket vectors, right? Because it's x here and x prime, right? So what we, okay, so let me do this carefully. So what we do here is that dx prime with the delta function and this x prime, when we integrate, what delta function does, it turns everything which has x prime to the x, right? By definition, the integral of x prime, f of x prime integrated with x minus x prime dx prime, this is just f of x, right? This is what delta function does when we integrate it with some function of a variable. So here the function kind of is this bra part of x prime. And so when we do this dx prime integration, we have only one integration left, dx. And then we have minus h squared 2m. Right? And then we note that this is identity, right? So we can put it or remove it. And so what we got back is just h in this form. Right? So we started with this form of h, and we got to the form where it's a familiar form of h. Right? So now, what this exercise helped us to do is to familiarize how to work with xx prime, and this is just one of the representations that you can use. So one of the useful parts is when you have several variables, and for some variables you use discrete representation, and for some you use continuous representation. Okay, so then you can get some advantage from doing that. I will show you in a moment.
The discrete representation,
which is if you have a discrete set of discrete but infinite set of functions,
okay.
right? So then you have a discrete summation for the resolution of identity, and you can represent then operator as I have it somewhere. Or maybe I deleted it. Essentially, instead of x's, you have fn's. Instead of integrals, you have sums, right? And that's one way. It's countable infinity, right? And this is uncountable infinity and continuous functions, where you have, in order to characterize the function, you have this continuous variable. Before you had the discrete index, now it's continuous function. And this looks like, essentially, this basis representation, also in Bryan-Ket notation. But when you start dealing with this, you can end up with the same form as you dealt before. Okay? Now one, I guess, note on the functions that probably are still quite weird for you, the functions of eigenfunctions of x and p, right? So this x and p, right? Their definition, as I said, that they are eigenfunctions, and the unpleasant part of working with them is that they are not normalizable, right? So that's one of the difficulties, I guess, measuring the position and momentum, because the spatial representation of x is delta, and if you form the delta x minus x prime squared dx, right, that's going to be infinity. And with p, it's the same story. So the p functions, if you do the x representation, those are exponent of pi x, right? And then if you do the integral of exponent ipx squared, it's also infinite because this is just a constant, right? And then you integrate the whole space and it becomes infinite. Why this is infinite? you can simply go by definition. The kind of the simplest definition of delta function is that if you have a function, right, then what delta function does, it essentially gets the value of the function. Like if you have dx here, right, then you get in the f of x. And for this case, what you're getting here, when you, well, delta function is a real function, so you can avoid the modulus. And so you have two delta functions. So one you can represent as a function, and another is a delta function. And what they do when you integrate, according to this definition, this integral will be just the delta function at x equals x prime, right? And this is delta at 0, and delta at 0 is infinity, right? So always, when you are in doubt, use this definition of what delta function does as an, sometimes it's called kernel of the integral operator, because there is no point of considering delta function by itself. The way you should think about it is as a kind of integral operator, whatever function you have, you put it in the integral with delta function, right? And then the action of the delta function on the function of your interest is given by this definition. All right, so okay, now what do we do next? Next. Sure, let's do a short break. All right, so I already started talking a little bit about the advantages of the state representation, because the main advantage is you're expecting that you don't need to go up to infinity here in these summations, and instead of working with, say, operators, you can work with the finite matrices, okay? Because as long as well, once you set up your functions, then this turns into the matrix, right? And it's finite matrix if this sum is finite, okay? So the interesting side, I guess, well, if you can afford to truncate the summation.
Like so we're making our solutions less precise by.
That's right.
Okay.
Well, you don't want to, if you don't know how to treat problem analytically, then there is no way you can, essentially work with infinite matrices, right? Numerically, it's impossible.
Because you don't have infinite coverage.
That's right.
Okay.
That's right. So then, why the truncation is possible? There is a simple argument that if, say, you work with function and you are interested in, well, I guess it's not that you're working with a single function, but if we restrict just an application of the operator h on the function psi, then one rationale why we can truncate this summation is that I already gave it to you in particle in the box example, that the way operator in this form acts on psi is through projecting psi first on the basis, right? So these coefficients, essentially coefficients of expansion of psi function in the basis of f and x, right? So if these coefficients, they're potentially infinite, number of these coefficients, but if they have kind of, this is the value of the coefficient, right? Absolute value, say, so that we can order them. And this is n, so if you have something significant initially, and then they become smaller and smaller and smaller, and you have 99.9% of the function represented with, say, 10 terms, then you don't need all the other terms, right? From 11th to infinite, you can throw them out, because simply operator in this form will not care too much about these other functions. Unless, of course, something terribly happens with, say, F11 basis function, right? The Hamiltonian acting on F11 actually quite large. So this function, the norm of this function is very large, then the fact that the coefficient in front of the F11 is small may not be enough, right?
How would you get such a large, like operating on like the 11th eigenfunction?
Well, it's very simple. Let's consider, to be concrete, let's consider H harmonic oscillator, right? And we have F, let's make F's solutions for the harmonic oscillator problem, right? So then HFN equals to n plus 1/2 H bar omega, right, Fn. So these are our eigenfunctions, energies. Okay? So what do we have? First of all, if we are expanding an eigenfunctions, that means actually this is even simpler. This becomes, instead of double summation, it becomes a single summation. So, because those are eigenfunctions. Do I need to explain this step, or it's obvious?
Sure.
Huh? No, please tell me, because
go ahead. Go ahead.
Yeah? Oh, if HFN is an eigenfunction that is constant Fn, so in a double summation, those two functions are different, but if H only produces a constant, then what we're going to get is this, Fn, Fm, and then the eigenfunction from the M part, right? But these guys, they are orthonormal, so you only get delta Nm when you make a scalar product, right? So that kills one of the summation indices, right? And then we have Fn, En, Fn, right? So that's the representation for Hamiltonian in the basis of eigenfunctions. And you can see already that with n, Ens, they grow linearly, right? So the fact that if you are dealing with a function where the coefficient, say, C1 is bigger than C2, it's not yet enough for discarding the C2 or F2 function, for that matter, because the constant that you need to multiply, well, the C2, it's E2, which is larger than E1. Right? So when you act with this Hamiltonian on the psi, then you get n, Fn, En, Cn, right? And then this is sum over n, Fn, and then n plus 1/2 H omega Cn, right? So the fact that the C1, say, larger than C2 doesn't matter, because if we call this Cn prime, then what is important is Cn prime rather than just Cn.
Yes, so in this case, the eigenvalues grow as the books go down. So
That's right.
You can't just forget about the hierarchy.
That's right. That's right. So you need to be careful here, but generally, the logic goes as follows. Most of the problems in molecular physics, right, and chemical physics, we know the energy range for these problems. Say, if it's a photoexcitation, say if we study vision process, right? So we know that we have a vision process under light conditions which are in a visible range, and that's between 1 and 3 electron volts. Okay, so this is our energy range, and there is no point if we have some idea what the harmonic oscillator, say, involved in the vision process, and we'll talk about that, like how harmonic models, say, can help us a little bit because it defines vibrations. Then you can roughly say what would be the eigenfunctions that are in the range of energy that we're interested in. Okay, and then since our physics in that energy range, our wave functions will be representable by eigenfunctions which are in that energy range. Okay, and that allows us, in some cases, or in many realistic cases, it allows us to truncate the summation, and it allows us to say, okay, what basis should we use to represent the operator, okay, in this matrix form? What will be adequate? Okay, because if we truncate it too much, then we have, say, a wave function. We need some function that is highly oscillatory. Oscillations means that the kinetic energy go up, right? So, and total energy goes up, but we don't have a function to represent this type of oscillations. So that means we're missing the component of the Hamiltonian that will tell us what will be the energy of that component, right? So we will underestimate something in our description, okay? But generally, this is useful because it allows us to present operator as a matrix. Okay. Now, I guess a little bit, since I'm not sure I'll be able to talk about the variational principle in length now. I just want to finish, I guess, this abstract representation stuff. So one interesting thing is that when we truncate the summation and go back to the space representation, what's going to happen? Because usually when you have an operator here represented as this is an infinite matrix, and that's exact representation of the operator. Now, in the practical applications, what we do, we can say we are always working with H tilde, which is summation over n. Let's make it... for simplicity, let's make it representable in eigenfunctions so that I won't have off-diagonal terms, right? So it will be Fn, Fn, and then En, right? And n goes from 1 to big N, okay? So this is only approximately equal to our original H, okay? Because we truncated the summation. Now, what will be, we know what this abstract H, how to put it in an X space. And that will be kind of local operator, at least potential part will be local. But now, what's going to happen with this? If we want to know how to represent this operator, truncated one, in the X representation. It's kind of interesting because this is, whenever you work with this Brian ket, it's kind of more abstract than this because this is a particular representation. Whenever you have a function psi, it's, I guess, simply because we're more used to work with normal functions in X space, right? So we have better intuition with them. So that's why it's important to be able to go back to whatever we are more comfortable with. So what happens here when we write the Hamiltonian as a truncated operator? What's going to be the X space representation? And to do that, we will do exactly the same as with the total operator. Just now, we'll introduce resolution of identity, okay, for H bar, and that will be okay. So. Okay. Then here we have Fn of x, Fn x prime, En Okay, and now to understand this operator, let's say we want to use it on a function psi, right? And we want to get the x representation of the result, right? Because when the h tilde acts on psi, it will generate us some phi tilde. And when we project on x double prime so that we distinguish that from those two x's, right? So then we'll get a more familiar phi x double prime function, right? Then we'll know what the effect of h on psi. So this will be
x prime there, and then
dx
in the bracket you have below. Is that
this
x double prime? Or
x double prime, yeah. So that's to distinguish those from the two x's here. All right. So x double prime. We will quickly start losing these different axes because we'll get some delta functions, as you will see in a moment. So that's integral x double prime goes with this x, and then x prime goes with this phi, right? And then there is a fn x fn star x prime en, and I also forgot here the n summation, right? So what we have is following. So we have x prime and we have dx prime. Okay, so this is a delta function, x double prime minus x. Okay, and that means when we integrate dx, we make every x to be x double prime, and we get rid of x double prime x. We integrate out the delta function. Okay, so we are left with x prime phi, which is just a phi x prime. We have n summation can be just put here. Fn x double prime fn star x prime en. Okay, and then we have dx prime. Okay, and this is our. Okay, so if this guy is psi, not phi, phi is the result. Okay. And the rest is, I think, okay. So, and this is our answer, phi x double prime. Now, what happens here is the following. We have this h tilde operator that we can say acts on psi of x double prime, because the result is in x double prime, and gets the phi x double prime, right? Now the way h operates, it's so-called integral operator. Sorry, there is an extra summation here. It shouldn't be there, right? So what it does, it has an integral over dx prime, and has this n over fn x double prime fn x prime. Okay, so then star, and it uses the psi and x prime inside and multiplies by en. And that's the result. So out of this integral, we can potentially take this, because it's x double prime variable. So it's sum over n f n x double prime dx prime fn star x prime en, and then whatever this operator is acting on, we put inside the integral, right? So if say we had function of psi x double prime, we put it inside of the integral, make it a function of x prime, integrate x prime, multiply by this fn, each component, which can be said is kind of some kind of dn. It depends on n, right? But it's a constant because we integrated all the variables x prime. And then we'll just get the summation of our basis functions, functions of x double prime, times these constants, and that will form our result, x double prime. As you can see, when you truncate and we go back to the x representation, our operator h tilde becomes the integral operator. So it's not anymore some differentiation or essentially multiplication by a function. What it does, it takes a function and puts an integral, change the variable, integrates out the x prime, multiplies by another function of the different, of the initial variable, right, and gives you a result. So somewhat non-intuitive. Okay, here nervous laugh, so it's time to wrap it up. Okay, what will be useful for our consideration of, say, molecular examples? And what was promised is that this going back between the basis representation and the spatial representation or continuous representation, it's useful sometimes, especially when we can locate the energy range. Yeah?
This may be a stupid question, but you went from having Fn and Fn to just having Fn.
Yeah.
How did that happen?
Okay, so the way it happens is that we assume that Fn is an eigenfunction of H.
Okay.
Okay? So H, Fn gives you, let's call it energy Fn, right?
Yeah.
Okay, then let's consider the original form Fn, H, Fm, and there's summation over Nm, right? So then H acting on Fm will give you Em, right? This is just a constant, so you can throw it out in front of the expression, right? So you get Fn, right? And this is a delta Kronecker because those basis functions there are orthonormal, right? So delta Kronecker means that only when m equals to n, then the term survives, right? And so we go from the double summation to a single summation, and we have Fn, and we get rid of this delta because it already played out, right? So we remove them. Yeah.
So if Fn is the acting function of H,
Right.
would you written on the right on that one? Should it be precisely equal to H? No,
It's approximate because in a harmonic oscillator we have infinite number, right? So here we consider the truncated case. Okay. And that truncation essentially, when we go back to the X representation, leads to all these complications with the way we represent the operator, because essentially we need to project and then integrate and then multiply by functions. So that's how it works, the projection in the continuous functions representation. Okay. All right. Now, imagine we have a situation where we have two-dimensional harmonic oscillator, And then the frequencies of this kind of those two oscillators that are uncoupled, right? So we have the Hamiltonian that is h of x plus h of y for now, and h of x, just h1 of x, is a normal px squared divided by 2m plus kx x squared divided by 2, right? h2 x. And imagine that kx is much larger than ky. Okay? What does that mean? Well, it means that the potential will look like this, right? More or less. So it's like ellipsoid shape. This is this will be the ky direction, y direction, and this will be the x direction. Right? This will be energy direction or the potential direction, right? So we have squeezed a parabola along the x, and we have very wide parabola along the y. Okay. Now we have these two variables, and for each we can solve. Say for each we solve in our harmonic oscillator problem, and so we're getting right solutions. Then we can represent our Hamiltonian. Currently it's represented as in the continuous variables, x and y space, right? But we can also represent them in the basis, right? So using these functions and this representation, knowing that since these functions are the fn's will be eigenfunctions for this and for that, so they also, their products will be eigenfunctions for the total. Is that clear, or do I need to explain why?
Yes.
Yeah, okay. So, and please try to remember this, because this point I will return to it in many cases, in many occasions. It's very important to understand. So if you have the case where your Hamiltonian or any other operator, it's separable, right, to sum of two operators. Yeah? It's just math, that's right. Okay, so then if you have functions which are eigenfunctions of each of these 1D operators, right? So
you have a set of eigenfunctions for one and a separate set for the other.
Right, then any eigenfunction for h let's call it k psi k x l y. Right, then any eigenfunction like this, psi k, is equal to fn1 times fm2. This is function of x, this is function of y. Okay, I think I even mentioned that before, maybe in one of these first lectures, when we studied going from the time-dependent to time-independent Schrödinger equation, right? So then x and y, x was x, y was time, right? And then there was this
as soon as you said separable.
Yeah. Okay, good. So this is an example of separable operators, right? And then the solution is constructing the solution is very simple. As long as you know the solutions for individual parts, you just make a product, and that gives you the eigenfunction. And for the corresponding eigenvalues, you just sum the eigenvalues for the, where was it? This is. n of 1 plus epsilon m of 2. Right? And that's very easy to show. You just take this product, put it in a total eigenproblem, then this guy will act only on its eigenfunction. The other eigenfunction in this product will be just a constant to it because it's y, and if it's acting on x, it will just take out the corresponding eigenvalue. And the second part will act on the y part, but won't take anything from x. It will just multiply y by constant, right? And so you have a product intact, and this sum in front of it. Okay, so I'm pretty sure you can just do it at home. This is very simple algebraic exercise. Okay, but this is the solution, right? Now, using these solutions, what we can do, we can represent the Hamiltonian as actually in 3 different forms. First, we already did. This is the first representation. Second is using the functions or their product. It's fn1, fm2. Here we'll have en plus e2 m2 fm2 fn1. One thing to remember is that never write x or y when you are in the Bryan-Cat notation, right? So the variable is not mentioned. Usually if your function depends on some parameters, then they mentioned in the parentheses. But variables will never be mentioned because to get the variable you need to project on them. All right, so that's one mistake people sometimes do. All right, anyway, so this is the second representation. What we did, we presented, essentially we used this, where is it? Yeah, it's kind of this representation, but now each term is just a product, okay? Because now for the 2D case, the eigenfunctions we need to use in this summation, they're product eigenfunctions. They're product of eigenfunctions for the first part and for the second part, okay? These guys are, if we go to the space representation, these are functions of x, and these are functions of y, okay? So we still have n and m because we have 2 variables, okay? But n and m are the same in the kind of bra part and cat part. That's right. Okay, so the only, I guess, complication of this case compared to the previous one is that now we have 2 variables, so we're using products. Okay? And this is the way to write it. Just, yeah, it's just a product. Okay, so this is the second. And then alternatively, we can use, well, actually there will be 4 representations, but third and fourth will be staying in continuous basis for one variable and switching to the discrete basis for another. Okay? And now you may wonder, why are we doing all this? And it all kind of is related to the fact that I set up the problem so that one dimension has levels that are further apart than than the levels in another dimension. Okay, so this En1 and Em2, they accumulate, like you accumulate energy by going with these discrete subscripts differently in 2 different dimensions. The one that is quite squeezed, the x direction, I believe, yeah. So the x direction, if you increase the quantum numbers in x direction, the energy, the total energy will go up pretty quickly, right? And if you go over the quantum numbers in y direction, the energy will go relatively slowly. Okay? So now, why is this important? It is important, again, because I said in many practical problems, you know what the energy range is, okay, for your problem. And if you know, like, most of the chemistry is a low energy physics, okay? So compared to the high energy physics, it's all very relatively low. And so imagine we're working somewhere in this range, or this and below. You can see that only 0 point energy in X is related to that energy slice we're interested in. Okay? So this level and the higher levels, they are just too high if we know that we're working in this energy window. Right? So then there is opportunity to switch to this state representation, truncate the summation for X basis to be just say few first states. Zeros, harmonic oscillator has 0 point energies, right? So it's n equals 0 and n equals 1, right? But for the y variable, there are lots of levels. So you can potentially either make different truncation for m index. If m is for y, then m, say, goes from 0 to 100, and n will go from 0 to 1. Okay? So you can truncate these things differently because you know the inherent energy scale of the problem, and you also know how much energy you are gaining by going over these states. Okay? So that's the main point here. Also, you can keep, for some problems, it's just a matter of convenience, before switching to some particular basis, maybe even keeping this in a continuous basis. You can do that too by essentially forming this Hamiltonian is HXY Hamiltonian. And if you only take states that are of the first variable, n states, right? So this will, here I should not write x and y because, well, variables, this is abstract operator, but these guys, so one, okay. This is an integral over only x variables for the fn x, h, which is x and y, right? And so this becomes a function, I'll call it h, that has y variable and has subscript n, right? Because it will depend on what basis function in x you use to integrate x variable of the total Hamiltonian. Okay? This will be some function. And then the Hamiltonian representation will be, we are left with this f1, right? And then there will be these functions h, y, sum over n, where n goes from 0 to 1.
Why, when we have the Dirac notation, and then we go down to the integral. Why is the integral over x? Why is that? Like, do we just choose that?
We just choose that we will discretize x direction. So we'll keep the x direction functions, right? But we'll have continuous y direction. We have a choice, right? So we can use different bases for different directions. Okay?
Okay.
Yeah. So it turns out that if we know that there are few functions we need to use in x direction, so that is advantageous to use then the discrete representation. Okay? And then actually that's what happens when we study molecules. The electron energy scale is much higher. It can be thought as x direction. The energy levels of electronic states, they are much farther apart from each other. These potential energy surfaces we'll be talking about later. They are separated. And then there is a nuclear degrees of freedom that have much closer energy spacing. Okay, so we have nuclear variables presented with the continuous variables, but electronic states are discrete states. And that's convenient representation because photochemistry, for example, can be described now as going from state number 1 as, usually it's S0, right, ground state, to S1, and maybe S1 is intersecting with S2 or S0, like rhodopsin case, for example, the mechanism of our vision. There, the levels are S0, S1, right? And these are two different conformations of retinal, the chromophore that starts the vision process. So the energy of the visible light gets us from S0 to S1. This is a big transition compared to the vibrational levels that are on S0 or S1. So it is convenient then to represent our total Hamiltonian as in this form, essentially, that we have S0 state, some nuclear Hamiltonian of S0 state plus S1 state, and then some nuclear Hamiltonian of S1 state, which is in continuous nuclear variables, right? And then some coupling terms, which we'll talk probably later. Because, of course, this is nice and easy to investigate, but the real chemistry starts when we add the coupling between those two directions. And that's usually the case. If we study electrons and nuclei, there is they cannot be, put together without the electron-nuclear attraction. Otherwise, electrons will spread apart, and then the nuclei spread apart, right? So then these two will not be really realistic or adequate to represent molecule if we consider this as a Hamiltonian for electrons and this a Hamiltonian for nuclei. Okay. All right. So I'll see you next time then, if you don't have any questions.